In this lesson, we're going to learn about bivariate data. We're going to learn to determine if there is a correlation between two sets of data by looking at scatter plots, correlation coefficients, and creating a linear regression model, also called a line of best fit, which we will write in the form of y equals mx plus b. So our line of best fits will be linear functions. We'll also learn how to interpolate and extrapolate using our line of best fit, also called linear regression model. So let's talk about bivariate data. We've been learning about univariate, where we have one variable involved, such as your average of your science grades or your math grades, or how many hours of sleep you get. Bivariate data is two variables. And the purpose is to explain if there is a possible relationship between the two variables. So for example, we could ask, is there a relationship between the number of gifted classes students take and students having all A's? So is there a relationship if you have more gifted classes, are you more likely to also have all A's? So how can we determine if there's a relationship? That's what we're going to take a look at in this lesson. And we're going to use scatter plots and lines of best fit to determine if there is a possible relationship. So again, scatter plots are useful to show if there is a correlation. So correlation, it is a measure. So it measures the strength of a linear association between two quantitative variables. So that's super important. So when we talk about correlation, we are referring to quantitative data versus qualitative. So we'll be looking at numerical values. That's how we can measure the strength. And all of our correlations we will be writing as linear functions, a linear association. So we're going to take a look at scatter plots. We're going to see if we do have a correlation. We will see if there is a linear association. So let's talk about correlation versus association. Sometimes folks use those interchangeable and maybe they don't use them correctly. So both of these terms are two methods to explain if there is a relationship between two statistical variables. However, association refers to a more generalized term when describing a relationship, where the term correlation, which is what we'll be using for this lesson of bivariate data, it is more precise term describing a linear relationship. It is what we call quantifiable. We can actually get a numerical value. We can measure it. So correlation can be considered as a special case of association, so a little bit more specific. So for example, if we said there is a strong correlation between hair color and IQ scores, well, we really wouldn't use the word correlation because we can't really quantify hair color. So we really should use the word association. So let's get into specific correlation. So there are several types of correlation, and let's take a look at two of them here. So a positive correlation just means that as we go from left to right on our graph, like we always do our data points in the scatter plot, do they seem to trend up or down, or are they scattered all over the place? So you can see that in our example number 1, the graph to the left, that these data points show a trend of increasing, having a positive slope. In our second graph, you can see there still is kind of a trend of as our x values increase, the y values are increasing too. They're just not as clustered as graph number 1. So graph number 1, we call it strong positive because our graph is moving in a positive direction, and they are clustered pretty close together, where in example number 2, it is still showing a positive correlation as the x's increase, our y's increase, but they're not clustered together, so we call that weak positive. So you may want to pause the video and write these 2 descriptions in your notes. And I will remind us that in a scatter plot, we do not connect the points. Now let's take a look at 2 more correlations. In graph number 1, the one to the left, we can see that as the x values increase, our y values decrease, giving us a negative correlation, a negative slope, so to speak. And these are clustered pretty close together, indicating there is a strong relationship between the 2 variables. The graph on the right, again, is showing a negative correlation. And we need to put a G here for negative. We do have a negative correlation. As the x values increase, the y values are decreasing, giving us that negative slope, but they're scattered and they're not as clustered as our example to the left, so we call it weak negative. So again, you may want to pause the video and write these 2 descriptions in your notes. Here's the last possible description of correlation when there seems to be no correlation. So for example, this graph on the left, there is no pattern as the x's increase, which is always how you prep your determination of correlation. You always say, as the x's increase, what is happening to the y values? So these are scattered all about. There's no pattern, so we call it no correlation. The 2 variables are not related at all. Or you could have a constant where as the x is increased, the y value is staying the same. So again, there's no correlation. So you may want to pause the video and jot these notes in your notebook. So when attempting to find a correlation, beware that, remember, correlation applies only to quantitative variables, not qualitative. While correlation can be calculated for any pair of variables, it only measures the strength of the linear association. So we're only looking at linear associations here. And then don't forget about possible outliers. They can distort a correlation. Correlation does not imply causation. So things may correlate with each other, but it doesn't mean that something actually caused something else to increase or decrease. It could just be a coincidence. For example, as the temperature increased, the ice cream consumption increased. So, when the weather gets warmer and we get more into spring, summer, we tend to maybe eat more ice cream, but the temperature itself did not cause us to go out and get ice cream. It may just be that we're kind of in the mood for ice cream now. Or as the time the students gamed, like video gaming, their exam scores decreased. So there probably is an association. If you spend more time gaming, maybe you don't study, or maybe it just might be that you don't do well on tests. So let's talk about regression analysis. So regression analysis is just the study of the relationship between pairs of variables, x and y. When this data is graphed, we create a scatter plot. And we want to know how good our line of best fit is. Our line of best fit, guys, is going to be our linear regression model. And we want to know how strong is that line of best fit? Does that line of best fit represent the data really well or not? So here again, we're going to look at slope-intercept form, y equals mx plus b. This is called linear regression model. It's called our line of best fit. Those terms are interchangeable. And we will be able to take this equation and be able to predict future data. So that is the purpose of a line of best fit or a linear regression model, is to be able to look at data that maybe sits outside of the data we've collected to make predictions. So based on the line of best fit, like I was just saying, we can predict other data. Now, here are two terms that you need to jot down in your notebook. Interpolate simply means, so you can remember the word enter. So interpolate is to make predictions which lie inside the data that you have sitting in front of you. Extrapolating is looking outside, looking at extra data outside that you don't have. And again, we will use our line of best fit to be able to answer questions and make predictions. So interpolating is inside the data we're given. Extrapolating is looking at data outside the data that we're given. Now, we do need to take note, the further away from the plotted values, the less reliable the prediction. So when we are looking at data points that are given and those data points that lie close to our line of best fit are going to be more reliable than data points that lie further away.